All right, part two. Still working on Extrema. In the last video, we talked a little bit about how this was basically an extension of previous knowledge in terms of what we talked about during our discussion of the analysis of polynomial graphs. What we have here in the derivative is a brand new, robust tool to use in order to evaluate graphs now in terms of if we're given the function. So let's go ahead and do one more polynomial before we sort of jump into more complex functions. And let's say we have f of x is equal to x cubed plus 9/2 x squared minus 54x plus 2. Okay? Still a cubic, still positive leading coefficient. You still know that it's going to be, whatever, because of the end behavior, you know that, whatever value you get as a critical value that's further to the left is going to be your maximum. Whatever's going to be further to the right is going to be your minimum. Now that's not going to be very helpful in terms of justifying your answer in terms of calculus, but it's always nice to know a little bit about the function before you enter in. Part of the reason why we concentrated so much on graphing over the past few years. Let's go ahead and take the derivative, and we're going to get 3x squared plus 9x minus 54. Okay? Now, you know that this is a polynomial, so you're not going to be looking for critical values where the derivative doesn't exist, because the derivative always exists, right? The derivative has the same domain as the original function, because all polynomial functions exist and are continuous on negative infinity to infinity. But we will be looking for critical values where the derivative is equal to 0. And of course, we need to very, very quickly go ahead and divide through by 3, at which point this factors very, very easily. And I'm left with x is equal to -6 and x is equal to 3. Those are your critical values. Now, since this is a polynomial, you know the shape of this polynomial, and you know that it's going to have 2 humps, and you have 2 critical values, you know that both of these are going to be extrema. But in the abstract, when you're dealing with any particular function, you don't know when you get down here and find out that the derivative is 0 at -6 and +3, that these are necessarily extrema. Okay, they could be like 0, 0 on the parent function of cubics, the y is equal to x cubed, right? It could be a point at which the graph comes up and lays flat for a split second before it keeps going up, right? Now remember that in order for a critical value to be an extrema, 2 things have to be the case. The derivative has to be 0 or undefined, okay? That's good. We've got them equal to 0 at these two. We've got it equal to 0 at these 2 points. And it has to change sign, okay? Well, those are 2 points, so that carves up the domain into 3 chunks. And we'll go ahead and deal with those 3 chunks. Chunks, very, very specific, very technical math term. Negative infinity to -6, -6 to 3, and 3 to infinity. Okay. Now you know that f prime, let's go ahead and draw a little line right here, f prime is going to be 0 at -6 and 3. That's how you found those values, right? Was setting f prime equal to 0. But you need now to evaluate the sign, the positiveness or negativeness on all of these intervals. Okay? Well, here's the thing. It's in factored form right here. So actually you know that f prime of x is equal to 3, x plus 6, x minus 3, right? And oftentimes it's easier to evaluate the sign of f prime if it's in factored form, right? Because, positive times a positive is a positive, and a positive times a negative is a negative, and all sorts of fun stuff like that. Okay, so let's take -7, and let's plug it into both of these factors. Now 3 is obviously always going to be positive because it's positive, and it's a constant, right? Plug in -7 into here, and we're going to get a negative. Plug -7 into here, and you're going to get a negative. So positive times negative is positive. So your slope from negative infinity to -6 is positive. And you know that the slope is going to be consistent on that interval because the only place that it can change is at a critical value, and you already identified the only two critical values for that particular function. Now let's go ahead and take a representative point on here. The obvious one is going to be 0 on that interval. Plug in 0 into here, you're going to get positive 3 times positive 6 times negative 3. Not so much worried about the actual value, but the signs, because 0 was not, it was only significant as a representative point of the interval, right? So let's go ahead and use 4. Plug in 4 into here, we're going to get 3 times 10 times 1. All of those positive. A positive times a positive times a positive is a positive, of course. And you see the fact that this has this general shape. And then you would just evaluate it, okay? You would say you have a maximum at x is equal to negative 6 because f prime changes from positive to, and of course I'm doing a whole bunch of abbreviations, because at that point f prime changes from positive to negative. And then you would say you have a minimum at x is equal to 3, okay, because f prime changes from negative to positive. And that is how you find out, that's how you identify extrema on a particular function. You take the original function, you find the derivative, you determine where the derivative is either 0 or undefined, you plop them into a sign chart, evaluate the intervals of the sign chart for the derivative, and then basically identify the places where the slope changes sign. And that is how you find extrema, okay? Let's deal with one that's a little more complicated than that, okay? Now, hopefully some of you will recognize this function. We've talked about it before. X over x squared plus 1. Now, if you're not remembering that particular function, let's go ahead and do a new equation. And you go x divided by x squared plus 1, and it looks something like that, right? It's called a serpentine function, okay? Because if you actually did that, right, 1 over x squared plus 1, it's just this hump right here because it winds up being an even function, right? But the moment that you change that numerator to x, that's odd over even, and it winds up being an odd function, okay? Now, obviously, right about here is going to be my minimum. Right about here is going to be my maximum. Those are going to be my critical values. Well, let's go ahead and actually find those analytically. Now, I know that f prime of x, okay, I'm going to have to use a quotient rule. The bottom times the derivative of the top minus, okay, the top times the derivative of the bottom, all of that over the bottom squared. Now remember, you're not looking here for a place where the derivative is undefined, because the only thing that happened from the original function to the derivative is that x squared plus 1 became squared in the denominator. And x squared plus 1 we know is always positive, right? X squared is always non-negative. Non-negative plus 1 is always positive. That's why this is a rational function that has no discontinuities, because that denominator is always positive. Well, that denominator is always positive. So the only hope we have is, of course, finding a place where the numerator is equal to 0. Well, that's going to be x squared plus 1 minus 2x squared, or 1 minus x squared, over x squared plus 1 squared, and we get 1 minus x and 1 plus x as factors in that numerator. Well, I know that that means that I have x is equal to negative 1 and 1 as my critical values. And of course, if you remember that as a serpentine function, you should recognize the fact that that's going to be your minimum and that's going to be your maximum. But if you didn't, that's still okay. It's going to be very, very easy to go ahead and evaluate these. we're just going to go ahead and use those 2 points to set up, again, a sign chart. Okay? And I know that it goes from negative infinity to negative 1. X is equal to negative 1. Negative 1 to 1. X is equal to 1. And 1 to infinity. And that's how I'm going to break up the number line. And I'm going to evaluate f prime at those particular places. Well, at the critical values, it's 0 and 0. Okay? Well, let's go ahead and plug in a representative point for this interval. How about negative 2? If I plug in negative 2 in here, I'm going to get 1 minus 4 in the numerator. That's going to be negative. Okay? Well, let's go ahead and plug in a representative point on this interval. By the way, the denominator is always going to be positive, so we don't even have to check it, right? The sign is going to be determined by that numerator. That's why we're only worried about plugging in for the numerator. So I plug in 0. 1 minus 0, well, that's going to be positive. And then, of course, since it's squared, the same thing is going to happen for the representative point that you plug in from over here as the one you plugged in from over here. Let's use the symmetrical point. Let's use x is equal to 2. 2 as our representative value. It's going to be 1 minus 4, or negative here. So this is negative, positive, negative. And then, of course, from here, and the thing is that as long, like, getting to this point is sort of where I want you right now. You'll learn as you go forward that the AP exam, they used to accept just the sign chart as justification for finding extrema. Like if they give you a problem like that on free response. But back in the 90s, I think, or maybe a little bit later, they changed the rule. And you actually can't, I mean, you can do a sign chart, but a sign chart is not sufficient as justification. You actually need to write it out like I did on the last problem. In order to identify this point right here, okay, x is equal to negative 1, well, first of all, I need to find the ordered pair, right? Negative 1 blank, right? And 1 blank, okay? Well, you just go ahead and plug in here, right? And basically, if you plug in negative 1 into here, you get negative 1 over 2, or negative 1/2. And of course, it's similar. If you plug in 1, you get positive 1/2. So I now have the ordered pairs. Okay, so I have a minimum at negative 1, negative 1/2, because f prime changes from negative to positive, okay? And of course you'd write something similar up here for this particular point. You say that this is a maximum at 1, 1/2. Sorry, that's a terrible, okay. Yeah, 1, 1/2. And you know that because f prime changes from positive to negative at that particular point. And if you know that, that's basically the justification for identifying those 2 points as your extrema for that particular function. Okay? Now, about now, some of y'all, because you're watching this video after your teacher has lectured on this, are saying to yourself, but she's been doing all these on closed intervals. Well, see, and that's fine, and I understand, and I've never understood that. Most of the books actually introduce extrema on closed intervals first. I've never understood that. I've always swapped the order and just dealt with critical values and extrema for a function not limited by a closed interval, and then backtrack to do it on a closed interval. And so since that's worked for me in the past, that's the way I'm doing it now. In future videos, I will do it on a closed interval. So if you're waiting for that, you know, keep on going. Okay, just trust me. I've gotten you this far. But that brings us to about 15 minutes. I'll do a couple more functions on the open interval, meaning on the whole domain of that particular function, in the next video. And then I think in the 4th video, we'll probably switch over to a closed interval. Maybe do a couple of videos on that, maybe 1 or 2, and then we'll move on to 4.2, which is actually an extremely important section for the AP exam. they absolutely adore that particular section and the theorem contained therein. And it'll sound pretty similar because it's one that I sort of foreshadowed a whole lot in the last 2 years. But you have that to look forward to. So I'm going to go ahead and close this video up right now, and we'll do a couple more, and then we'll move on to 4.2.